In this section of notes, we'll be looking specifically at graphs for accelerating objects. We're going to warm up, though, by looking at a graph for a non-accelerating object. Here I've got a distance. Actually, I should call this a position time graph. Position is measured in meters, and the letter that represents position is an X. We always put position on the vertical axis and time on the horizontal axis. So the first question is, find the distance traveled between 0 and 2 seconds. So this is a little bit hard to see, but if I zoom in, I can see 1 second, 2 seconds, 3 seconds, 4 seconds, 5. I'll just label it so I have got it. And between 0 and 2 seconds, the object is remaining at a distance of 5 meters. So the distance traveled is 0 meters. All right, next, find the velocity between 9 and 15 seconds. So 9 seconds is here. 15 seconds is here. Now, 9 does not hit at a convenient spot. It doesn't hit at a crosshair. But what I do see is that the slope is the same between 8 and 15 seconds and between 9 and 15 seconds. The slope is the same all the way down. And let's see, this is 6, 7, 8. This would be a rise of -8 meters and a run of 7 seconds. So the velocity there would be -8 over 7 meters per second. Find the velocity between 5 and 8 seconds. Between 5 and 8 seconds, the object, again, is not moving, so the velocity would be 0 meters per second. And finally, it says find the average velocity for the entire interval between 0 and 15 seconds. So at 0 seconds, my initial position is 5 meters. And at 15 seconds, my position is 0 meters. So average velocity is change in position over change in time, which is final minus initial position, over final minus initial time. So that would be, let's see, 0 minus 5 over 15 minus 0. So that's going to be -5/15 or -1/3 meters per second. Okay, so that was a good warm-up. Now let's look at a velocity time graph. It looks kind of the same. It's got some horizontal segments, some diagonal segments, but this is a velocity time graph instead of a position time graph. And let's just go back to the simulation that we were looking at in our last notes. And I'm going to switch to charts, and I'm going to see what happens when I start our friend here at a position. Start him back here. I'll start him at a position of -10, and I'm going to give him, I'm going to clear these charts. I'm going to give him a velocity of 1. And you can see what the position time graph looks like, and the velocity time graph is horizontal. Now I'm going to give him an acceleration. A small acceleration. And notice what happens when he accelerates. Here's the section while he's accelerating. The position time graph is quadratic. The velocity time graph is a diagonal, and the acceleration time graph is a horizontal line. The slope, so this is my position time graph. the slope of this graph is velocity. This is my velocity time graph, and the slope is acceleration. The other thing that's kind of neat about this is we'll see in a moment that the area under this velocity time graph is going to have meaning as well. So I encourage you to play with that simulation. Let's go back to this example. Find the displacement between 0 and 3 seconds. Once again, I'm going to label my x-axis completely just to make my problem solving a little easier. Okay, so between 0 and 3 seconds, the object is traveling. Here we've got a speed of 4 meters per second, and that velocity is not changing. So I know that displacement is equal to velocity times change in time. This height of 1, 2, 3, 4 meters per second, that's my average velocity. And this width, that's my delta t. So the area of this rectangle is comprised then of 12 squares. And each square represents 1 meter. And the area underneath that graph represents displacement. So the displacement between 0 and 3 seconds then is 12 meters, and I showed my work over there. Find the acceleration between 3 and 6 seconds. Well, the acceleration is going to be slope. I'll change colors. So let's think about this for a second. This object has an initial velocity of 4 meters per second. And at the end of this interval, it has a final velocity of 7 meters per second. That means we have a rise or a change in velocity. Well, that's kind of hard to see, isn't it? A change in velocity of 3 meters per second. And that happens over a period of time of 3 seconds. So the slope of this line is the rise over the run, or the change in velocity over the change in the time, or 3 meters per second per 3 seconds, which is 1 meter per second squared. And that's the acceleration for that interval. When does the maximum speed occur? Well, during the next interval, this entire time here between 6 and 11 seconds, we have a speed of 7 meters per second, and it never gets any higher than that. So between 6 and 11 seconds. And then we'll find the displacement between 3 and 6 seconds. So again, the displacement is going to be the area. Now, I already figured out this area on the left. I know that that red area will also be 12 meters. The area of this portion will be half of 9, would be one way to get it. It's 4.5 meters. But I'm also going to take a moment to think about what this would be in terms of a trapezoid. So I'm going to erase some of my work here. This is a trapezoid. It's a trapezoid turned on its side. When you learned about trapezoids in geometry class, you learned this: B1, B2, and a height. And you learned that the area of a trapezoid is 1/2 the height times B1 plus B2. Now really what this is that the area is 1/2 B1 plus B2. That's the average of the bases. And then times the height. And maybe you see where I'm going with this. In this case, the bases are the velocities. This first base is the initial velocity, and it's 4 meters per second. The second base is the final velocity, and it is 7 meters per second. And then the height of this trapezoid, because this trapezoid is sort of turned on its side, the bases are vertical. The height is the change in time, and it's 3 seconds. So to find that area is 1/2 B1 plus B2 times h. And let's think about what these variables are. B1 was v naught, B2 was the final velocity, and h is delta t. Well, this is an equation that we've already learned. This is an equation for displacement. Anyway, when we solve it, get 1/2 4 plus 7 times 3. So that would be, let's see, 33 divided by 2. 16.5 meters. Again, this 1/2 B1 plus B2 is finding an average. Another way to think about it is to think about what would happen if you took the average of 4 and 7. Right down the middle would be 5.5, an average speed of 5.5. If we took this triangle and moved it here, you would end up with a rectangle with the same area, and therefore the same displacement. Okay, let's try 2 more examples here. We've got the same 2 graphs, but now we're supposed to convert the displacement time graph to a velocity time graph and convert the velocity time graph to a displacement time graph. So I know that the slope, this should say position. The slope of an x versus t, or position versus time graph, is velocity. So I need the slopes here. Horizontal line has a slope of 0. This slope is 1. This slope is 0, and I think I did this one already. The other one is -8/7. This is -8/7. Okay, so when I do this conversion, and I'm going to change the scale a little bit just to make it a little bit easier for myself. Let's see, 1, 2, 3, 4, 5. We'll call that 1. And we'll call that -1. Okay, so this is velocity in meters per second. This is time. I'm going to draw in some dotted lines to keep myself on track here. Ugh, that looks terrible. Hang on. I'm going to have Notability help me out. There we go. Okay, so I'm going to draw in some dotted lines. Keep myself on track. There we go. Okay. Now, the slope for the first 2 seconds, oops, I should have changed back to solid. The slope for the first 2 seconds is 0. The slope for the next 3 seconds is 1. The slope for the next 3 seconds is 0, and the slope for the final 3 seconds is -8/7, which is a little bit more than 1. Now you may be wondering what happens in between these points. This is actually technically impossible. We can't have a change in velocity in no time. Sharp corners on a position time graph, again, are technically impossible. If I go back to this graph, even with my simulated walker here, I'm going to hit clear on this. I'm going to have him, let's see, we'll start there. We'll have a negative speed. Oh, I will have him do a really small speed there. Okay, so here he goes. I'm going to have him slowly walk to the right. If I apply an acceleration, I'll apply a negative acceleration. Look at that position time graph. Do we ever get a perfectly straight line? See the curve in the position time graph? That's really much more realistic than having a corner or a point. You can't turn around in 0 seconds. Okay, let's look at this one then. This is the same graph that we did above, and we figured out that this was 12. Let's see what else we've got here. This area is 5 by, so this is 35 meters. This is, I figured this out. Where did it go? What was it, 16.5? And this final piece here, this area would be, it's a triangle, so 1/2 base times the height. The base is 2, and the height is 7, so that's just 7. Okay, so when I go back, what I know here is that this velocity is constant. The velocity is 4, which means the slope that I sweep out up above must be constant. Okay, let me do a little more thinking here to plan this out. I'm going to add all of these numbers together because I need to make a scale up above. So I'm going to add 12 plus 16.5 plus 35 plus 7, and I get, I'll make my scale about 75, 80. Okay, so we'll say it's 10, 20, 30, 40, 50, 60, 70. Okay. In the first 3 seconds, so to get to that point, the object travels 12 meters. So 12 is a little bit above 10. And this slope would be 4. Okay, now for the next segment, the object travels a total of 16.5, which is going to put it at 28.5. So 28.5 is almost to 30. Now here's the thing though, the slope starts at 4 and it increases. Look what velocity we end at. We ended at a velocity of 7, which means this portion is going to curve up. This has a slope of 4. This has a slope of 7. Okay. In the next segment, the object has a velocity of 7, and it travels a total of 35 more meters. So I've got 28.5 plus 35. So it's going to get to 63.5. So it's about here. And the slope there is about 7, is exactly 7. And then finally, the velocity goes to 0 in 2 seconds. And as it does that, it covers 7 meters. So we're going to wind up at 70.5. But the slope needs to curve to 0. So remember, this is a position time graph, and the slopes on this graph would give me the velocities on this one. Let's do a couple of more examples here. Let's say I have a position time graph that looks like this. What would this represent? This would represent an object standing still. It's not changing its position. It's staying at the same position. So the velocity of that object would be 0, and the acceleration of that object would be 0. Let's look at another situation. So we've got position time, velocity time, acceleration time. Let's suppose that the object did this. So this object has a positive velocity because it's got a positive slope. When I would graph that, it would look something like this. It would be positive constant velocity, positive constant slope, and that's how it would look on the velocity time graph. Acceleration. The slope of a velocity time graph is acceleration, and the slope of this graph is 0. So my acceleration would be 0. Let's try another one. What if it looked like that? Here, the slope is negative, so the velocity is negative. And the acceleration, again, is 0. Do a couple more. What if we have a changing slope? Here, the slope is 0. Again, this is my same 3 graphs. Here the slope is 0. Here the slope is positive. And remember, slope is just, in this case, another word for velocity. So the velocity starts at 0 and then increases. Now my acceleration finally is positive because the slope is positive. What about something like this? This has a slope of 0. This has a negative slope. So we would start at a velocity of 0, and it would become more and more negative. The acceleration here would be negative because the slope of the velocity time graph is acceleration, and it is a negative and constant value. So with all of these situations, let's go back to where we started. We look at the slope that gives us velocity. the slope of a position time graph. The slope of a velocity time graph gives us acceleration. That's it for today's notes.